So when we dissolve sodium chloride in the water, what we're basically doing is we're breaking this ionic bond and we're replacing it with new bonds between sodium plus and the partial negative charge of oxygen. This forms a bond. Not only one, but sodium is basically surrounded by water, by about 6 to 8 waters. So it's completely surrounded by what we call a cage of water. And the same thing happens with the chloride ion, except it doesn't interact with the oxygen, it interacts with the hydrogen. Because remember, the hydrogen is a partial positive charge, so it does the same thing. So the chloride ions and sodium ions, instead of interacting with each other like they do when it's a solid, they are now what we call solvated. They are surrounded by solvent, and the solvent is water. And that is a chemical reaction. Because we have broken an ionic bond and we have made these new bonds. So not all bonds are ionic and covalent. There's a lot of other ones. Those are the two major ones. Later on, we'll learn about metallic bonds, and these are intramolecular interactions. We'll learn about those. But basically, anything that where there's energy between different atoms is a bond. And so this is a bond, even though they're not really sharing electrons. It's based on a weak interaction with these ions, a positive ion and a partial negative. So it's a fairly strong interaction. So what about this reaction? So this is another one we're going to be doing tonight. We're going to take sucrose, solid, that is C6H12O6, and we're going to put that in water. What's going to happen to that one? Is that a chemical or a physical reaction? What do we think?
Physical?
Okay, why do you say that, Kimberly?
Because it's just like dissolving. It's not, you're not adding any other like chemicals in it.
Exactly right. Excellent. Yeah, sucrose doesn't break down. The reason is sucrose is not ionic. So when sucrose dissolves in water, it stays sucrose. It's a covalent compound. When it goes into water, it stays a covalent compound. It does get surrounded by water, of course, because if it didn't get surrounded by water, it wouldn't dissolve. But it doesn't break any of these. It doesn't break any of these chemical bonds when it goes into water. So that is physical. Because basically it has changed. It's gone from a solid into a dissolved state, or you could call it a hydrated state, because it's surrounded by water, but it has not changed chemically. So that's the main difference. So when we're doing our experiment tonight, this, like, the major background here is basically what are the difference between them. So over here, it gives you an idea that physical, whoops, get back here. That a physical change may look different. Like a physical change may involve a change in color, but does that mean that it's a change in chemistry? Like, for instance, if you mix blue and red together to make purple, Is that chemical or physical?
Physical?
Yeah, that's physical, because that's what you would expect. If you took a blue filter and you put a red filter in front of it and then looked at a light, you'd see purple. But nothing chemical has changed. Nothing chemical has happened. So that's a physical change. So change in state is the most obvious one, just going from one phase to another. But the H2O in water and steam and ice is identical. It's all H2O. There's no difference in it chemically at all. But when a chemical change happens, there are a number of things to look for, as in it produces something. The most obvious is it produces a gas. Something starts bubbling. That is the production of a new substance that wasn't there before, right? So if you, for instance, if you pour the hydrogen peroxide on a cut and it starts bubbling, it's producing oxygen gas. And that wasn't there before. It is now. And so that is a chemical reaction. What is a precipitate? Anyone give me a sort of a, what does that mean? You produce a precipitate. Have you heard that expression before, precipitate? Or precipitation? What does precipitation mean?
Something that is rushed?
Rushed?
Absorbed?
What's like the most common thing you think of when you hear the term precipitation?
Rain?
You think
Snow?
of rain, right? So what does rain do?
It comes down?
It falls, right? And that's what a precipitate is. Is a solid that falls out of solution. So like, and you'll see that a lot of times when you take a clear solution and another clear solution and you pour them together, and then boom, a chemical reaction takes place and some solid starts falling to the bottom. Generally, that is a highly ionic compound. Usually, not all the time, but it's generally a very, very ionic compound with a lot of charge density. Something like calcium +2 and phosphate -3. You put those together and get them in next to each other, and they really stick together hard. And they stick together so hard that they can't, that water can't break that bond like it can with sodium chloride. Sodium chloride just has one charge +1, -1, that's it. Water can break that one. But when you have +6 and -6 together, that really sticks together. Water cannot break it. And so it just falls to the bottom as a solid. That is clear evidence of a chemical reaction taking place. Another one is light being produced. That is really common, actually. Like, think of a fire. Light is being produced. That comes with the movement of electrons. That's where the light comes from. Electrons moving up and down in those energy levels that we've been talking about for like the last week or so. An excited electron gets pushed up into the energy level from where it normally sits. Like normally if an electron is, say, in the second energy level, and it absorbs a ton of energy and gets pushed into like the 7th level. Well, when it comes back down again, it emits light. And so that is usually because a chemical reaction has taken place. The production or the absorption of heat. What kind of reaction gives off heat. It produces heat. You remember? Something thermic. Thermic meaning heat. Do you remember from the old days what kind of reaction that is?
Thermal energy?
What is it?
Thermal energy?
Right, so it releases thermal energy. But what kind of reaction do we call it? We call it a something thermic reaction. Starts with an E. Followed by an X.
Exothermic?
There you go. Yeah, exo. Exo meaning going out or outer. So that means exothermic, meaning heat is being released to the outside. So if you are doing a reaction and you feel that the beaker or whatever you're doing the reaction is getting warm, or you see the temperature rising, that's an exothermic reaction. Heat is going from the reaction into whatever it is you're doing the reaction in, generally water or whatever. But what about when the heat flow goes the other direction? Heat goes from the water into the reaction. So the temperature goes down. Heat is actually absorbed. What kind of reaction do we call that? That also starts with an E.
Endothermic?
Endothermic, exactly. Endo, the opposite of exo. Endo means inside. So like an endoskeleton and an exoskeleton. So endo means inside, meaning the heat goes in. And so it actually gets cold. That's how you can get a cold pack. You know, when you like twist your ankle or something, someone gives you a cold pack and you break it, what happens is that there's a chemical in there that dissolves in water. And when it dissolves in water, it absorbs heat. Where does it absorb the heat from? It absorbs it from you, is where that heat's coming from. And so the heat goes from your swollen ankle into that reaction and the temperature goes down. And a color change. I know I just said that, you know, you can get a color change as a physical reaction, but that's one where, let's say you have two colorless chemicals and you mix them together and then boom, they turn blue or they turn green or they turn yellow. Something that you can't explain by just, you know, the simple color wheel. Like, you know, I added something yellow and I added something red and it turned orange. Well, duh, what else would it do? This would be like I had something yellow and I had something orange and I put it together and it was purple. Something that completely unexpected. So you can't explain that. So generally that's because some new chemical that didn't exist in either one of these solutions has been made and it's a different color than either of the starting materials. So these basically suggest that a chemical reaction has taken place. So hopefully you've read this because there is a lot of experiments going to be doing. There's a whole bunch of different things you need. And the things that you need, hopefully, because you read this already, that aren't in the kit, you need some water, quite a lot of water, actually. You need 1 gram of sugar, and you need 2 grams of just of simple table salt. You need an ice cube. Ooh, I gotta go get an ice cube. Some matches or a lighter or something, and then some sandpaper or something we're just gonna rub up a nail. That's going to be our source of iron in one of the reactions. So why do you think on a nail, why would we have to, it's made of iron, why would we have to scrape it with sandpaper in order for the reaction to take place? Who else does iron react with? What happens to iron what happens to the iron nail if you leave it out if you leave it outside?
It rusts.
It rusts. And what reaction is that? Who's iron reacting with to form rust?
Water.
Nope. Water helps. Water helps that reaction along, but it actually isn't the water that's doing it. The water helps catalyze the reaction by bringing bringing a surface that allows iron and the thing that it actually reacts with to come together. What's the thing that reacts with to make rust? Or what's another name for rust?
Oxidation? Nope.
Yes, that's right.
Oh,
You got it. It's an oxidation reaction that reacts with O2 and it forms iron oxide. So on the outside of a nail, most likely is a very, very thin coating of iron oxide. And so that iron, it's not going to be iron. It's going to be iron ion. It's going to be either iron +2 or iron +3. And so for the reaction we're going to do, we need iron itself. We don't want the ionized version. And so there's a really thin layer on the outside. That iron's already reacted. It's already reacted with oxygen. And so you'll notice that when you scrape it up, it gets shiny. That's because you've scraped away the oxide layer, and now you have nice shiny metal. The same thing is true when we do the reaction with magnesium. Unless the magnesium ribbon, it comes in a thin ribbon. Unless that magnesium ribbon has been kept under nitrogen or something, it's going to be oxidized. And so magnesium oxide is going to be on the outside, and it's kind of dark color. And when you scratch that up, you get this nice shiny metal again, because you've replaced the magnesium 2+, you've scraped that away, and now you just have simple magnesium there. And that's what we want for the reaction. So hopefully you get all this stuff together. That's a lot of stuff. Yellow food coloring. So hydrochloric acid. So goggles are essential tonight because we're going to be using hydrochloric acid, sodium hydroxide. Everyone's freaked out by acid, but actually it's the base that's more dangerous. Because I mean, the acid may burn you a little bit, but like I said before, the base will actually dissolve your skin. So that's not good. So be careful with that. If you want to wear gloves, that's fine. You don't have to, but just be careful with it. And copper sulfate, not really dangerous, but if you get it on, it's blue. And if you get it on your skin, it'll stay blue for quite a long time. So unless you want to look like a Smurf, that's probably a good idea to be careful with that as well. Anyone tell me what this one is? Phenolphthalein. What's that? And the rest of them are kind of food coloring, magnesium, yeah, whatever. But phenolphthalein, what is that? Has anyone heard of it? What does it do? I'll give you a hint. It is an indicator. But it's an indicator of what exactly? What does it indicate?
Oh, yo, pH. Yeah, I remember that.
There
from high
you
school.
go. Man, you're crushing it. Yeah, pH. Cool thing about phenolphthalein is when it's in acidic pH, which is pH less than 7. So neutral pH is pH 7. And low pH is acidic. And when it's acidic, it's colorless. When it's basic, when the pH becomes greater than around 8 or 9, it turns bright pink. And so it gives us an indication of what the pH is. And pH is just a concentration of how much H+ there is in solution. If you have a high amount of, that's what the H is in pH. It's what's the concentration of H+ ions in solution. Acid releases H+ ions, and bases generally absorb them. So when you dissolve an acid like hydrochloric acid in solution, it releases a lot of H+, pH goes down, and the phenolphthalein is clear. When you put sodium hydroxide in, sodium hydroxide soaks up the H+ and turns it back into water. And so the pH goes up and it becomes basic and it turns pink. All right. So let's just quickly go through some of these reactions that we can get started. Because we're going to be doing a lot of them, but they don't really take a long time to do. The thing you need to look at is be careful with what you're doing. Read the instructions, slowly and carefully, understand what you're doing. And you need to really pay attention to what's happening. You need to pay attention to the temperature. That's one of the things we're going to basically measure for all these things. We're going to be measuring the temperature with a thermometer and seeing if it goes up or down, seeing if it's an exothermic or an endothermic reaction. We're going to be looking at the production of color, and yes, it's spelled with a U, the proper way. And we're going to be looking to see if precipitate is formed. And we use the shorthand PPT, or chemists will also make an arrow pointing down. So like, for instance, this reaction. I'm just going to go keep using calcium and phosphate because I've made so many of these stupid solutions where it would precipitate. So it makes Ca3PO4, 2, and then you put an arrow next to it indicating that it fell to the bottom of my vessel. It precipitated. So you're going to be looking at all those things and to see what happens. Oh, and also, of course, looking to see if light is produced. So we're looking to see if the temperature goes up or the temperature goes down. Is a color produced? Is light produced? Is a precipitate produced? All those things. You need to be paying attention to what things look like before and what things look like after. So it's important that you have a notebook with you in order to write down anything. Like, are bubbles being formed? Do you notice, is there something you smell? You may, because a gas may be produced that you can't really see, but maybe you can smell it. And if that occurs, if you smell something that wasn't there before, well, that's probably a chemical reaction too. So the first one is going to be HCl. What's HCl? What is that? I just wrote that down. What is that?
Hydrochloric acid.
That's right, hydrochloric acid. And it's called that because when I take HCl, which is a liquid, and I dissolve it in water, what happens is that this bond breaks and it get released H+ and Cl-. And what we put next to the H+ and the Cl- is this. Can anyone tell me what this means? Brackets AQ.
Aqueous?
That's right. It means it's in now and it's in an aqueous solution. Excellent. And remember, it's the production of this in water that causes the pH to go down. And that leads to it being an acidic solution. So it's that reaction which leads to acid being H+ being produced. And HCl is a strong acid. We'll learn this a little bit later, I think. HCl is a strong acid because when you dissolve it in water, all of it dissociates into H+ and Cl-. When you have a weak acid, like acetic acid, which is vinegar, basically, when you put that into water, only about 1 to 2% of it becomes H+. So it's weak, which is good because you wouldn't want your, really good rice vinegar or something to completely dissolve your food. You just want a little bit of it to dissociate, to give it a little bit of flavor, but you wouldn't want the whole thing. So for this one, we're going to take test tubes, put them in the rack. Hopefully everyone has everything together. I've got my stuff getting ready. And we're going to we have a 10 mil graduated cylinder, smaller than the 50, hopefully, at about 2 mils. And so when it says 2 mils and not 2.0 or 2.00. Don't worry that if it's not exactly 2. If it's 2.2 or 1.8, that's close enough, right? Horseshoes, hand grenades, and a single significant digit just means you just got to get it close. So we're going to look at what happens when we add hydrochloric acid to sodium carbonate. So remember, we're going to test, we're going to mix them together, record the color this goes on in the data table. Tonight's report is really pretty simple. You're basically just reporting exactly what happened. What did these things look like before? What do they look like during? What do they look like after? And then what happened based on what you saw. So for this one, just mix them together, check to see if it changes color, check to see if it changes temperature, and see if any precipitation or anything else has occurred. So for that one and all the other ones, when you're done, just dump them into the large beaker, and that can be just poured down the sink at the end of the night, because we're not dealing with anything dangerous. Like, even though hydrochloric acid is kind of nasty, when you dilute it with water, it's no biggie. So that's the first one, and I think hopefully these are all pretty much the same. So what I'm going to do is move my camera. I'm going to get ready. I want you guys to get, if you haven't read the activities and the procedure, you're going to be in trouble, because we're going to be doing all of these tonight, one right after the other. Okay, so are there any questions about any of these activities? Because of course everyone's read it already. Everyone's got their goggles on.
Yes,
All right.
do
Oh, go ahead.
you want me to turn my camera on?
Yes, I do.
Okay.
Because yeah, I want to see that people are actually doing the experiments and aren't setting themselves on fire. Okay, so I'll do some of these with you. I'm probably not going to do all of them, but I'll do some of them with you. The ones that you like, if you have some real questions about them, I can give you some guidance on how to do them, but I'm not going to do all of them. So I am going to stop sharing, and I'm going to get my stuff ready. So I'll see you in a second. All right, getting all my stuff together. Man, it's kind of tough arranging all the windows to see you guys and see the instructions. And all right, so this is the test tube holder. It really comes in handy, because when you're doing reactions with these things, you don't want to be holding them in your hand, right? So what's a good idea is just, you find this, it comes looking just like flat, and then you just pop it together. And you can put them in the end and then actually see what's happening. Because if you look at it like that, that's going to be kind of hard. So let's do the first one. So the 10 mil graduated cylinder is this cute little one right here. So cute. And there's a good suggestion in the instructions, which of course everyone's read, about your thermometer. So the thermometer has this little rubber ring on top of it. And you may wonder what the hell that rubber ring is for. It's basically so it doesn't roll off of your table. If you find that isn't big enough, just get yourself a rubber band and tie it to the top. Yeah, now this thing's not going anywhere. And you can also always move the rubber band around so that when you put the thermometer into the test tube, it doesn't go all the way to the bottom. It just sort of hangs close to the bottom, but not quite. So handy little chemistry hint for y'all. All right, so my 2 mils of hydrochloric acid. Most of the acids and bases come in this chemistry kit number 2, I believe. Yeah, set number 2.
Yeah, that's where I found all of mine too.
Yeah. And the nice thing about these is that they have a dropper so that you're not pouring it. You don't want to be pouring this stuff, but you could use it as a dropper, so it goes 1 drop at a time. So it's great for 2 reasons. So it's, you're not pouring it, you're not going to splash it around, and it helps you be a little more accurate. First I should make sure there's nothing nasty in my 10. I'm just going to give it a quick rinse with some water just to be on the safe side. Okay. And remember, when you're measuring things, you want to hold up the cylinder up to eye level so you can actually see what it is you're measuring. So I'm going to hold it up to eye level so I can see. There we go. So always replace the cap when you're dealing with these kind of nasty things. Pour it in test tube 1 here. Then it says to rinse the graduated cylinder 3 times. Sounds like a lot, but all right. Yeah, basically they don't want any HCl left in there. So the next time you use this, it won't start a reaction in your graduated cylinder, which is not a bad idea. Okay. Now looking for my sodium carbonate solution. Oh, that was another bag. Yeah, that is in the exploring physical and chemical changes bag. There's a whole bunch of different bags. I must have spent about 20 minutes this afternoon looking for all these things. All right, so sodium carbonate 1M. What does that mean? Sodium carbonate 1M. Anyone tell me what that is? Have you heard of that before? What does 1M stand for? I'll give you a hint. It's a concentration. What do you think the M stands for? What have we been learning about recently?
Is it molar?
It's molar. Excellent. What does molar mean? Do you know?
Concentration.
It's a concentration. And the molar kind of gives it away. What do you think the concentration is in?
Moles like per liter or something like that?
Exactly.
Yeah.
Excellent job. Yeah. When we're doing reactions in solution, it's much easier to measure volumes than it is to measure masses, right? Because we just measure, this is super, super easy. So what we want is to be able to know how much reactive stuff is in this solution. And so 1 molar means there's 1 mole of it for every liter of solution. Great job. So I got HCl in one test tube, and I've got sodium carbonate in the other. So record the temperature. So when you put the thermometer in, leave it there for a good, like 2 minutes or so. If you have a digital thermometer, that works even better. So you don't have to use this thermometer. If you have one of those fancy digital thermometers that you use for cooking, I've got one upstairs for grilling meats or whatever else. Use that, because that's a hell of a lot easier than reading this. So it should be approximately room temperature, right? So whatever your room is. So I'm looking at it. And again, you're going to want to record this to 3 significant digits. For instance, it's not enough to say it's 19 degrees Celsius. If it's between 19 and 20, then you have to estimate. Where is it? Is it 19.2, 3, 4? That's going to be an estimate. If it's exactly on the 19, then say it's 19.0. So always use the precision that comes with your instrument. So I'm looking at this, and looks to be right on the 21. So I would record this as 21.0. So then I write 21 for HCl, 21.0. I can even give the thermometer a little rinse because it's got HCl on it. And then I record the other. And it pretty much should be the same temperature, but we want to make sure. All right, I check it. And it is indeed the same temperature. 21 right on the nose. So I take it out. And now I'm going to put these together. So you want to pour it in quickly. Don't. And then get the thermometer in as quickly as possible. Now I'm just going to see what happens to the temperature. So a couple things happen. Who's done this reaction already? What happened when you put them together?
Made a sizzling sound.
It did, right? Anything else happen?
I saw bubbles.
Yes. So what is that? What do you think that's an indication of?
Heat.
Bubbles are an indication of heat? Why do you say that?
Because it reminds you of like boiling. Ay, ay, ay.
Well, you can get
But there's a
bubbles
chemical
without,
reaction.
you can get bubbles without boiling, though.
True. You can get. I think it's like a chemical reaction, though, right? Like that's happening.
Could be.
Yes, there is 100%.
But when you shake up soda, it releases.
Okay, that's us.
It
Yeah,
releases
gas,
gas.
CO2.
Is that physical reaction or a chemical reaction?
Physical.
It's right. It's a physical reaction because the CO2 is already there.
Yeah. All
And
you're
it's
doing
just
is
going,
just
it's just going from CO2 aqueous to
to
CO2 gas.
G gas.
Yeah. But what happens to the temperature? I'm looking at it and it may have gone up a degree, but it's not a dramatic difference. But let it sit for a couple minutes. What you want to do is keep looking at the temperature, and you want to record the highest, because basically if you left this here for 3 weeks, eventually it would go back to the room temperature, and you'd say, well, nothing happened. So the temperature is going to go up from the reaction. The reaction, if it's an exothermic reaction, that heat is going to go into the solution and heat it up. Then eventually, what happens to the heat in the solution? Where does it go? Is that just going to stay hot indefinitely? Anyone?
No.
No, it's going to be lost, right? It's going to go from the solution into the walls of the tube, and then into your hand, and then into the room, and so eventually everything will come back to the same temperature. All
Professor,
right.
a question.
Okay. Yes.
For the sodium carbonate, is it the same as sodium hydroxide?
It is definitely not.
Okay,
Because it
they
doesn't-
gave me
because
a
it
bottle
doesn't-
of sodium hydroxide.
because carbonate ion and hydroxide ion are completely different.
Okay, well, I think there's a problem in my kit. They gave me sodium hydroxide instead.
You have both.
Okay.
You have both. The carbonate is in the bag saying exploring physical and chemical changes. It's in a different bag.
Oh, okay.
Yeah.
Oops.
Yeah. Sodium carbonate is similar to baking soda, which is sodium bicarbonate, which is exactly the same as sodium carbonate, except it has an extra hydrogen.
Okay.
So what do you think that gas was? Carbonate. Anyone know what the formula for carbonate is?
CO3.
CO3, right. So what do you think that gas was?
Oxygen.
Try again.
No.
If you have
CO2.
CO2, that's
Yeah,
right.
my bad. I.
Yep. That's what happens with baking soda. That's why, you put baking
Oh
soda
yeah.
in
Mhm.
something, and it tends to, rise things, make things a little bit larger, because of this carbon dioxide gas
Sodium bicarbonate.
being
Ooh.
released. All right, let me rinse these out. Do the next one. I want to do the fun one with the nail. I'm gonna have to go look for some. I'm in the garage, so I'm pretty sure I must have some sandpaper nearby. So that's a fun one. That's number 2. Yeah, the sodium hydroxide is in a bigger bottle. The sodium carbonate is in a smaller one.
I'm still looking for it. Yeah, I'll let you know. I'm kind of worried right now.
Oh, I mean, yeah, it is possible you know, they missed one. That happens sometimes. Yeah, this one is tricky. There's so many different things to do. Oh, there it is. Yeah, the sodium polyacrylate is in a bag. I kept looking for it in a different size container. So again, when you're weighing something like that, you put the weigh boat on your scale first, and then tare it with the right button so that you get zeros. And then sodium polyacrylate. I've never used this stuff before. I'm kind of curious to see what it looks like.
This brown stuff that they gave us with some of the acids, can this be used
Used
the
for,
sandpaper as like the sandpaper texture?
oh no, that's not, that's very, very soft. That's for if there's a leak, it sops up any excess liquid.
Oh, I see.
Yeah.
What if you have like a nail file?
Oh, for the sandpaper? Yeah, that works.
Okay.
Yeah, anything that's scratchy.
And are we expected to finish this all tonight? Because there's like 11 activities.
Well, I mean, each one of them only takes about 5 minutes, so
Oh, I see.
should be able to, but if not, you know, you do what you can. Okay. Yeah, the sodium acrylate is a polyacrylate. It's a nice white powder. Doesn't look too dangerous or anything.
Yeah, I haven't found it. I have tons of sodium hydroxide, but no sodium carbonate in my kit.
You have the bag saying exploring physical and chemical changes in there. It should come with the nail and the tin pan.
Ah, found it.
There you go. All right, so here's my sodium acrylate. Again, when you have a weigh boat like this, just squeeze it together, and that helps you put the solid into the tube. Just give it a nice little tap. Okay, there we go. And my 10 mils of water. Okay. So you record the color of the contents, like the color of water, nothing. And then I've got this nice white powder for sodium polyacrylate. So I take the temperature of the water, and it probably hasn't changed since a minute ago. But I want to leave it in there for about a minute or so. Now it's a little bit less, about 20.5 degrees. So make a note of that. Then I just add the water, the sodium acrylate. Here we go. I haven't done this, kind of looking forward to it. So you can see it is now, it's not clear anymore. Not only that, it would appear that this is indeed a phase change. Because it is, does anyone know what we would call this phase? It's not just a solid. We would give this a different name.
Substrate?
Hmm?
Substrate?
Subtrene?
Wait, substrate? Or no?
Substrate is just a chemical that you're doing a reaction with.
Oh, okay.
But this, you can see, has changed so that it's,
Yeah.
and you probably see these sorts of things all the time, like Jell-O.
Gelatinous.
Yeah, it's called a gel.
Oh.
Yeah. Basically, it's a suspension of solids in a liquid that expand, so that the solids expand and take up all this space. Because really, there's only 0.3 grams of solid in here in 10 mils of water. So there's 10 grams of water and there's 0.3 grams of solid, but the whole thing's a solid now. So we call that a gel because it's almost all water. So this one, you basically just have to throw this one away because you don't have to worry about like cleaning this out or anything. You can just toss it. That was cool. Kind of difficult to monitor the temperature change though. All right, so I'm going to do number 6 with HCl or hydrochloric acid and NaOH, sodium hydroxide. OH, remember, is a polyatomic ion. Both the oxygen and the hydrogen are chemically linked together, but together they have a charge of -1. Okay, number 6. Two mils of sodium hydroxide. And sodium hydroxide is in a much bigger bottle. So you can tell should always read the label before you use anything. But it's very easy to make the mistake of sodium carbonate, sodium hydroxide. Well, they both say sodium, right? Yes, but they're completely different things. And the sodium hydroxide comes in a much bigger bottle. And again, be careful with this stuff. You do not want to splash it on your hands. If you do splash it on your hands, go directly to a sink and just rinse them for about 5 minutes. All right, 2 mils.
Professor.
See,
So like, for the experiment, right? For each activity, right? It says place 2 test tubes, right?
yeah.
Is it like saying new test tubes, right?
Well, just rinse them out. I mean, the only one you
Okay,
really can't
I
rinse
could just
out-
like, I could just like rinse it out in the sink, right?
Of course, yeah. Pretty
Okay.
much the only one you can't rinse out is the polyacrylate because that made a gel and that's not going anywhere.
It's
So,
gonna
That
clog
one's
up.
that one's
yeah.
getting tossed, so
Thank you.
no worries.
Professor?
Yes, a question, Amy? I can't see you.
Oh.
In fact, there's a bunch of you that I can't see.
Which activity are you on right now?
I'm doing number 6. I'm
Oh,
gonna
so you
do-
skipped 3, 4, 5.
No, you can do them in whatever order you want.
Oh, okay.
Yeah.
Thank you.
For the when you measure the temperature, do you have to wait like a minute before you put it in the water, acid or base or anything?
Well, when you put the, so right now I've got my 2 mils of 1 molar sodium hydroxide in here. I put the thermometer in and I let it sit there for about a minute.
Oh, okay.
Yeah, because I want it to, although all these things have been in this room for like at least a couple hours, so they all pretty much should be the same temperature, but you want to make absolutely certain. So while I'm waiting for that to just rinse out sodium hydroxide and then do
Professor, I have a question.
see. Mm-hmm.
Sorry to interrupt.
Yes, what's up?
Oh, never mind, never mind. I figured it out.
Man, that was quick.
I know.
All right, my sodium, my hydrochloric acid, put that in a new tube. Again, 2 mils. Okay.
And you said for the thermometer, the temperature, you wanted it 3 significant digits, correct?
Right.
Okay.
Yeah, so if it's exactly 19, you write down 19.0. If it's exactly 20, it's 20.0. But if it's in between, then it would be 19 point something. And that's sort of up to you to make that determination. And I can rinse off my thermometer.
And you just rinse off the thermometer with water, correct?
Yep.
Okay. And they said do it 3 times. It's like rinsing out the beakers 3 times.
Yeah, I mean, that's just for you know, making sure you're doing it correctly. All right, so sodium hydroxide. So I'm going to add a drop. Now, the phenolphthalein is very, very brightly colored. So you will see color change take place very fast. So the phenolphthalein is in ethanol. It is an organic molecule that doesn't dissolve super well in water. So it's in ethanol, but 1 drop of it should stay in solution. Here's my sodium hydroxide, and I put 1 drop in and watch the color change. Just mix it up. You can see it turns this bright pink color. So what does the bright pink color? Notice the phenolphthalein is clear. It doesn't have any color. And the sodium hydroxide didn't have any color. But we mix them together and we get this color. So what does that tell us? It might be easier. Yeah, definitely easier to see with against a white background. So if we have 2 clear solutions and we get a pink color, what does that tell us?
Really acidic.
No.
Wouldn't it be that a chemical reaction occurred?
That's right, a chemical reaction occurred. But remember, I'm following these directions here. So I have my sodium hydroxide solution and I put a drop of phenolphthalein in there. Now I'm going to check the temperature to see if any heat was released. I'll just leave that there for a minute. And the temperature does not seem to be rising. We'll leave it there for a minute just to make sure.
We put the hydrochloric acid with the sodium hydroxide, right? Or have we not?
Explain that. I don't understand that question.
Never mind. I think I got it.
I mean, you put them together eventually, but you don't mix them together until the part B. So checking the temperature again and bupkis. I'm not really seeing anything. So give this a rinse again.
I noticed sometimes for some of them, you have to leave it in for like 2 to 3 minutes and then the temperature will,
Oh, yeah.
rise. Yeah.
Yeah, because I'm pretty sure this is an exothermic reaction. So we should see a temperature change this time. So here is my, oh wow, it's actually become a little more dilute. So there's my pink solution of phenolphthalein and NaOH, sodium hydroxide. There it is. And then here's my clear solution of HCl. We can even put another drop of phenolphthalein in. Just so we can see the color change a little more clearly. You're mixing liquids in a test tube. You don't want to shake it. Basically, you hold it by the top, and then you sort of just smack the bottom of it gently. And that way the solution doesn't go everywhere. So you can see now I have a much more brightly colored solution. So I should be able to see the color change much better. Right, so sodium hydroxide plus phenolphthalein. So this is a basic solution. Remember, basic means there's a pH greater than 7. 7 is neutral. So I put my HCl in. And what happened to the color? Gone.
It went clear.
And then put my thermometer in, because I have my suspicions that this is probably exothermic. Oh yeah. So probably, I don't know if you can see that or not, but the temperature's gone from 22 to 26 in just like about 30 seconds. So I'm just going to leave it in there, and then every couple seconds I'm going to check it again. When it gets to the highest temperature, that's the one I'm going to record as 26, 26.5. 27. Yeah, this is where a digital thermometer would come in super handy. But then I guess these kits would cost too much, so they're already about $360. All right, now the temperature's starting to go down. So I would record that as whatever the highest temperature was. So for me, mine was 27. It's now down to less than 26. So that reaction, the heat has gone from the reaction into the solution, and now it's going from the solution into the surroundings. So that's as high a temperature as I'm going to get. So that reaction is done. Anyone know where the fun little side note here? Anyone know where the heat comes from in that reaction? So I'm going to write down the reaction. So the reaction is that's the acid. This is the base. And they make water. That is called a neutralization reaction. Because you can see that the H plus just hooks up with the OH minus. The hydroxide just shares a couple of electrons with the hydrogen, with the proton, the hydrogen ion, and it makes water. So is the heat from breaking bonds or making bonds?
breaking.
Okay, what bonds am I breaking in this reaction? It's a really difficult concept for students to get because it's really kind of confusing. Am I breaking any bonds here? Am I breaking bonds or making them? So I'm going from H plus and OH minus, making
Isn't this-
water.
A synthesis reaction?
Oh, it'd be making.
Yeah, you can consider it a synthesis reaction because I'm taking two different things and making a new thing out of it. So yeah,
Oh, then you're making.
I'm making bonds.
Yeah, you're making bonds because you
That's right.
created
I'm
H2O, right?
I'm making an oxygen, a hydrogen bond in that reaction.
Mm-hmm.
And yet it's releasing heat.
Mm-hmm.
And so you actually get energy released when you make bonds. That's the kind of trippy thing, because when you burn wood, you expect that you're getting energy out of it by breaking the bonds in the wood, right? But you don't. That actually takes energy to break bonds. You get the energy from forming CO2 and H2O in the reaction. You actually get the energy when you make the products. And that's really difficult for people to wrap their heads around. I know it took me the longest time to that doesn't make any sense, But when you think about it, you need to add energy to something to break it. It just doesn't break on its own. You have to do that. All right. Let's see, copper sulfate and NaOH. Probably handle that one. Blue and yellow water. Pretty sure you can handle that one. Oh, this is a fun one. Okay, so the magnesium and HCl. That's a fun reaction. So I'm going to have to find some sandpaper. So I will be right back. Oh, scheiße. No.
Professor, I have a question.
Okay.
For my like measurements, they're all staying the same. I don't know.
Which
Like-
measurements?
Like I'm putting like my thermometer like in it,
Mhm.
and like my thermometer isn't going up or anything. Like it just stays like, I don't know, like it stays
For
at, like,
all, for every reaction, even the hydrogen, even the HCl and NaOH?
yeah. I mean, it goes up a little bit, but it's not going up like a lot.
Well, if it goes up a little bit, that's enough.
Oh, that's enough. It doesn't have to go up a lot. Okay, thank you.
Yeah, these things aren't gonna rocket up to like 60 degrees or anything.
Okay.
Yeah, these are fairly, like mine just went from like 21 to about 26.
Okay. Okay.
Does that sound about right?
Yeah, sounds about right.
Okay, yeah. You're not gonna see anything, we're not gonna, because anything that exothermic would be dangerous.
Okay, I
Because
would.
If you,
I know.
if it's an extremely exothermic reaction, it could explode. So we
Okay,
don't
I
want
was just
that.
making sure my thermometer doesn't go up.
Yeah.
Thank
All
you.
right, so. And hydrochloric acid and magnesium, number 9. This one is cool. We use this actual reaction. I don't know if we're going to do this experiment later this term or not, but when we measure the when we look at the gas laws, there is a constant that puts all the gas laws together, like that involves the number of moles of gas, temperature of gas, pressure of gas, all, and it relates all those things together. And we actually calculate it using this reaction. So it's a real easy one to do, and it's fun to watch. So I want my 5 mils of HCl.
Sorry to interrupt. For
No,
activity two,
interrupt. That's the whole point.
for the sodium poly
Acrylate?
late,
Mhm.
it says pre-wave. So do we just pour the whole thing into the other test tube?
Pour what whole thing?
The whole thing of the sodium poly.
Did you weigh out 0.3 grams?
Okay, that answers my question.
Yeah. Don't pour the whole 2 grams. My God, it'll form concrete. So man, we're going through a lot of hydrochloric acid. I think there's only what, like 20 mils here. You really got to squeeze it to get it out. There we go. So remember, all these are approximate. So if it says 5, don't sweat a little bit more, a little bit less. If it said 5.0, pay attention. Right, so here's my test tube. Put my HCl in there. And then measure the temperature. So while I'm letting that come to temperature, so you should have some scissors and cut yourself off a small piece of the magnesium ribbon. So you got lots of magnesium here. Magnesium is a really nice metal. It's very nice and light. Can make lots of fun things with magnesium. So just a little piece, doesn't have to be exactly half a centimeter. But what you want to do is, if you'll notice, if you look really closely, it's shiny, but it's not super shiny. It's kind of got a, what we call a patina on it. You probably heard that term before, patina. That basically means oxidation. Like if you have patina on old things of brass or old silverware, gets a patina. That's just a fancy way of saying it's oxidized. So just get yourself a piece of sandpaper. I've got a piece of sandpaper here, and just rub it up a little bit. Because basically what you're doing is now we're removing that magnesium oxide layer that's on the outside. because oxygen is super reactive. That's why we breathe it, basically, because it reacts with so many things in our body. And notice when look what happens when I rub it on the sandpaper, look how shiny it is now. It's super shiny. Okay, so I checked my temperature. Again, pretty much the same temperature it's been all night, 21. Take the thermometer out, and then we toss. Now it's really important you have your goggles on for this, because watch what happens. So it immediately starts to bubble. So we put our thermometer in and we swirl it. And you may notice that the metal is not sinking to the bottom. And so you might be tempted to say, hey, this magnesium is not as dense as water. But that's not what's holding it up. What's holding the magnesium up in our solution? What's preventing it from sinking to the bottom? You can see the shiny piece of magnesium there.
I think it's because of the density of the hydrochloric acid.
Nope. Although that's not a bad guess. That's actually a pretty good guess. And now it's gone.
Oh, maybe it's because of the chemical reaction between the hydrochloric acid and the magnesium, right? So like because
It's not just the chemical reaction, but if anyone's doing this at the same time, there was something that was completely coating the magnesium metal. What was being produced in this reaction?
A lot of bubbles.
A lot of bubbles, a lot of gas.
Yeah.
And whoa, the
temperature. Oh, and gases float, so maybe that was why.
Yeah. So it was surrounded by gas. And the temperature went super high this time. Oh man, I should have. Oh, damn. So my temperature in my solution went up to, whoa, 35 degrees. So from 21 to 35. So we had more than one indication of a chemical reaction for that one. So in your reports, when it says, whatever, your conclusion, is it a chemical or physical? You got to explain why. Don't just say, it was the chemical reaction. I've noticed that now they've started grading some of your lab reports. You need to explain why you do things. Like for instance, the first lab, one of the questions was, why do we change the y-intercept to 0? And a lot of people just wrote down, because it gives you better data. And that's not an answer. You have to explain why. Why does it give you a better answer? So same thing here, like which one of the observations you made tells you that it's a chemical reaction or tells you that it isn't. Be specific. Okay, yeah, I like that one. All right, copper sulfate and sodium chloride. Okay. So hopefully everyone's brought down some salt. I brought down some salt from the kitchen and just put it in one of these little containers and just labeled it NaCl. Because, you know, salt and sugar right next to each other, kind of hard to tell which is which. Although sugar crystals should be, even if it's like really clean white sugar, should be a little bit yellow, just a tiny bit. And generally, that's how you can tell the difference. Obviously, you could stick your finger in and taste it, but that's not really a good habit to get into when you're trying to identify chemicals.
For experiment 2, did we make salt like ice or something?
Was it cold?
No, but it like solidified to like a gelatinous kind of substance.
You made a gel.
Pretty cool.
Yeah, you made a gel. So yeah, a gel is a suspension of a solid in a liquid, where the solid expands to take up a huge amount of space. So believe it or not, like 97% of the mass in here is water.
Huh.
Right? Because you have 10 mils of water, that's 10 grams, and you only put 0.3 grams. Yeah, so it's 99.7% water by mass. So
to figure out the accurate temperature, do we have to stick it all the way to the bottom?
yeah, it doesn't have to touch the bottom, but you want this whole red part, the whole red part of the thermometer to be submerged.
Okay.
Yeah.
Okay.
All right, so I'm gonna get my 2 tubes. So 5 mils copper sulfate. So copper sulfate is this bright blue. So why does it have copper 2 sulfate? What does that mean? Notice right on the label, it says copper 2 sulfate. What's the 2 stand for? There's 2 coppers? Well, there's 2 sulfates. What does that refer to? I cannot find the chat. Oh, there it is. All right, so copper 2 sulfate. What does the 2 refer to?
The charge.
The charge of what?
Copper.
Charge of the copper. So what's the charge of the copper in here?
2+.
2+, exactly. So just like the sodium chloride, when you dissolve it in water, the copper is now free in solution as a 2+ ion, and the sulfate is free in solution as a -2 ion. If they weren't, you would see solids at the bottom, but we don't see any solids at the bottom. So that means that all of the salt, and copper 2 sulfate is a salt, any mixture of a metal and a non-metal, we call that a salt, is all, if it's all dissolved, that means it's all in solution as an ion. So copper 2, interestingly, copper 2 and copper 1 are different colors. And it all has to do, because color, remember, all comes from electrons. Everything comes from electrons. And so different number of electrons in different places give you different colors. So let's see what happens in this one. So you want 5 mils of it. Yeah, copper 2 is a really pretty blue color. Like that sort of sky blue or Carolina blue. All right. 5 mils goes in there. And then I record the temperature. Here's my blue. So now I want 2 grams of table salt. I'm going to make sure I haven't mixed up my salt and my sugar. Here's my salt. So I want 2 grams. Hopefully I brought enough. Yeah. That goes into test tube number 2. Right, so I got salt in here. Sodium chloride in one. I've got my copper sulfate in the other. I'm checking the temperature, 21 degrees, like everything has been. Pour the copper sulfate into the sodium chloride. I can already see something happening at the bottom here. And I start swirling, 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 swirling. And I put my thermometer in. Now, you can definitely see 2 things have happened. There is something solid appearing in the bottom of the tube. And I don't think it's NaCl because it appears to be a different color. If you look really closely, it appears to be like almost a brownish yellow color. Sodium chloride isn't that color. Sodium chloride is white crystals. And as much as I try mixing it, nothing's happening. Check the temperature. Temperature is not changed. So I can try stirring this with something else. Here I've got a pipette, I can try stirring it with that. If I was in the lab, I would use something called a vortexer, which would spin this at a really high speed to see if I can get into the solution. I can also mix it with mixing it up and down. And notice, doesn't really matter how much I mix it up and down, it is not going into solution. Sodium chloride, on the other hand, is sodium chloride soluble in water?
Yes.
Yeah, it's super, super soluble in water. You could dissolve a metric butt ton of sodium chloride in water. But this stuff is not going back into solution. So, do we write down what the temperature change was? Did we see a color change? Note the color before and after. What color was the copper sulfate before? Before I added the sodium
It's
chloride.
like blue.
It was blue. What color is it now?
It's like turquoise.
Yeah, it's turquoise, it's kind of green.
Oh yeah.
So this is a different form of copper. Something has changed. Something has changed here. So these are the things you actually you can. I guess there's not really room in the report. I should have left some room to actually take some pictures of these things and include it in your report. That would have been a good idea. Because you could really see the before and after. That's a really pretty green, actually. And I'm pretty sure that's copper 1. Copper 1 is like a green color. Copper 2 is a blue color. So I'm going to save that because we're going to use it in activity 11.
When we dispose of the, once we clean our equipment and stuff, we can just dispose it in a sink or toilet or whatever, right?
Yep.
Okay.
Yep. All right, so going to 11. We have an aluminum dish here, but you can use, if you just have some aluminum foil at home, you can use that too. Doesn't really matter. This is a cool reaction too. We just cut up some pieces. So, you make a note, gee, what does aluminum looks like? It's silver colored and shiny. You see, aluminum, one of the nice things about aluminum and why, one of the reasons why airplanes are mainly built out of aluminum, 2 reasons. One is aluminum is super lightweight. And so obviously you want airplanes to be as light as possible. You wouldn't build them out of lead that never get off the ground. Aluminum is also super strong. And if you notice how shiny it is, it doesn't really rust. Like magnesium rusts pretty quickly. You can see that the magnesium ribbon was pretty tarnished, but aluminum doesn't really tarnish. I mean, it does, everything tarnishes eventually, but very, very, very slowly. So measure the temperature of our copper sulfate sodium chloride solution. I believe it is the same as it was, 21 degrees. Yep. Okay. So now I'm just going to drop the pieces in here. This is a cool reaction. And pay attention to what happens to the aluminum. We're getting yet another thing being produced this time.
That looks nasty.
It is nasty. Basically, what we're doing here is we're copper plating the aluminum. What's happening is copper is taking the place of the aluminum. We can also see some other things happening. Note that gas, getting some bubbles as well. But yeah, it's really cool when you have a lot of this and you take just a big piece of aluminum foil and just toss it in there. Yeah, it looks gnarly as hell. And we're going to learn about these reactions a little bit later. These are called redox reactions or oxidation reduction reactions. And what those are just electrons being transferred from one element to another. So what's happening here is that we have pure aluminum, so just aluminum with no charge, aluminum metal. And we're stealing its electrons and turning it into aluminum +3. Those electrons are going to copper. So copper was +1, and now it's going to copper 0 or copper metal. And that's the brown color you're seeing. This copper metal. So the aluminum is going from being a charge of 0 to a charge of +3. We say that's being oxidized because its electrons are being taken from it. So its charge is going up. We say that the copper is being reduced because its charge is going down. Its charge is being reduced. Its charge is going from +1 to 0. So we say the copper is being reduced and the aluminum is being oxidized. Most reactions are redox reactions in one way or another because they involve electrons moving from one place to another. And that's what we're doing right here. Yeah, it's ugly, but it's kind of fun. Okay. So bring on the nail. I want to do the nail. Oh, forgot to record the temperature. Bad, professor. Kind of tough to get the old thermometer in there. Oh dear. You will see that this is exothermic as hell. Because if you feel the side of the tube, it is warm. This is an extremely exothermic reaction. Temperatures like above 50, 51. Yeah, just feel the side of the tube. It is warm.
Geez, this one's the hottest one yet.
Yeah, that's very, very exothermic. That's because basically you have aluminum losing 3 electrons, and it's much more stable as a +3 ion than it is as just metal, aluminum metal. And so when it loses those 3 electrons, it becomes much, much more stable. And the difference in stability is reflected in the heat it releases. So when something becomes very, very stable, it releases a lot of heat. Cool. So that one's kind of gnarly to clean. This comes out in a big clump. All right.
Hey, Professor, is it possible to save some of this stuff?
To what?
Save some of this stuff?
Save it?
Like activity 1. It's pretty cool to, because it's not like you can actually discard it. I mean, you'd have to discard it with the tube.
Oh, you mean the gel?
Yeah.
Activity 2. Yeah, you can hold on to it if you want. And it's not dangerous or anything.
Oh, okay. Can we eat it? No, I'm just kidding.
Probably, but I probably wouldn't. Actually, if you want to know that, read the label.
Huh.
Because if it's dangerous, it will tell you.
Oh, I see.
It says not for food or drug use. So yeah, I think it's, yeah. Yeah, it says not a dangerous substance according to the classification. So yeah, I think it's actually used in some food production.
Oh.
But yeah, I wouldn't.
Have you been to Canada College in San Mateo?
I have not.
If you go to the science building, up on the hill is a private property where 3 llamas are.
Oh, that's awesome.
Yeah.
Oh, I have been by Kenyatta, actually. I don't think I've seen the, I think I had to get my picture
My
taken
teacher
there.
named it Cusco, Yzma, and Pronk
Oh yeah, I've heard of them.
from the Emperor's New Groove.
Yeah, I think I had to get my ID picture taken there. So that, yeah, that was a while ago. But yeah, I missed the llamas, man. That would have been awesome. All right, so here is my 5 mils again. So I got my beautiful Carolina blue, copper 2 sulfate. And instead of magnesium or aluminum this time, we're going to use iron in the form of a nail, which is in a bag here somewhere. Here it is. It's going to be a huge cleanup after this one. So it's already pretty shiny, but 2 reasons to polish this are that a lot of nails will have like a thin coating of something on them to keep them from rusting. So they could be, like they're called galvanized, which basically just means running electricity through it and then plating it with something that doesn't rust as easily. Or it hasn't had that happen and it has a thin layer of iron oxide on it. Either way, we want actual iron. So we're going to clean this off. So I'm just going to sand the tip of it. Right, so you can see it's nice and shiny at the end there. So that's what we're looking for. We want just the pure, clean iron metal. So remember, when iron is a metal, what's its charge? What's the charge of the iron when it's a metal?
Positive.
Is it? Look at the title of the, it says copper 2 sulfate and Fe. Is there any charge next to the Fe?
No.
No. So what's the charge? What's the charge of iron metal?
0.
0, right. It doesn't have one. Iron is only charged when it's an ion. These are made, this is made of iron atoms. So they're not charged. It's a neutral atom. Because if it was made of ions, it would just fall apart, right? Because the ions would all repel each other and it would just fall to pieces. So there's no charge in this. So here is my beautiful blue sulfate. I'm going to drop my nail in there and I'm going to watch what happens to the temperature. I'm going to put my thermometer in there and then watch them both. I do see the temperature going up a tiny, tiny bit. Remember, not all reactions happen at the same rate. Some reactions are very, very fast, like the neutralization reaction we did with these HCl, the hydrochloric acid, and the sodium hydroxide. That happened like that. We saw the change in color of the phenolphthalein was instantaneous. And we saw that when we put the aluminum foil in with the copper sulfate, that reaction happened pretty quickly. But if we look at this, there's no gas being produced that you can really tell. There might be a little bit at the bottom. There may be a few bubbles on the nail. It's kind of hard to see. But it says to allow it to remain in there for at least a minute. Yeah, if we do this experiment again next term, I think I'll definitely have to make room for before and after pictures to really, that would really help. All right, so it's been in there for at least a minute. So we're going to take the nail out. So the temperature go up by about 2 degrees, not a lot. Where are those forceps? Here they are. So use the These are called forceps. Enough nurses in here know what forceps are. It's pretty useless at getting out the nail, I have to say. There we go. So we look at the color of the solution, and it really hasn't changed much, but look at the nail.
Jeez.
You see what happened to the nail?
Rusted.
It didn't really rust.
Well, like, change color.
It definitely changed color, right? What that is most likely we have copper plated the nail.
That's so cool.
So just like the aluminum before, we basically, the aluminum and the copper changed places. The aluminum was a metal and the copper was an ion. And then the aluminum became an ion and the copper became a solid metal. And the same thing is true here. The iron has swapped places with the copper. So some of the copper ions from solution are now stuck to the iron, become metal, and turn some of the iron into ions, which then went into solution. So that's another oxidation reduction reaction. Yeah, that was not quite as dramatic as the aluminum, but so it basically tells us that copper can steal electrons from both iron and aluminum. And that's one of the things we'll learn a little bit later about the periodic table, is how we can look at it and determine, we can predict what the activity of these metals are. Which metals can steal electrons from other metals? Because that basically this is what happens inside of a battery. So in a battery, you've got two different metals, right? You've got lithium, nickel, or you've got lead, aluminum, or something like that. So what happens is the electrons are just going back and forth, back and forth, back and forth. One of those metals steals electrons from the other metal, and you recharge the battery by sending in electrons and forcing the reaction to go backwards. And then you let the battery run and electrons go in the other direction. So that's all you're doing, is just moving electrons in one direction, but then electrons in the other direction. And eventually one of the metals just completely gets used up and you got to get a new battery. So, all right, I'm going to move back to the desk and be here to take any questions from folks. I'll be right back. Oh dear.
So the difference between like a chemical versus physical, a physical is like it can change form or change shape versus a chemical, an actual new substance occurs or there's a breaking of a bond or
Yes, that's the whole thing right there, is that you've made a new substance. In a chemical reaction, you created something new. Like for instance, when we put the copper sulfate and the aluminum together, we took aluminum metal with a charge of 0 and we converted it into the aluminum +3. And we took the copper ions that were in solution and we turned that back into copper metal. So things that weren't there before were created. And so that chemical bonds were broken and made. Electrons basically went back and forth between different elements. And anytime electrons go back and forth between elements, that's a chemical reaction. Chemical reactions are just electrons moving back and forth. That's it. Yeah, so all the physical ones we've looked at, yeah, like you said, changes shape, still the same molecule. Change in state, it went from a liquid to a gas, still the same molecule. So that's one of the things that high school students have a really hard time imagining. They think that when you boil water, the gas that comes out is hydrogen and oxygen. And we know that's not true, because if it was, our kitchens would be blowing up on, you know, on the daily, right? It's still water. It's just in a vapor form.
okay.
Yeah. So how's everybody doing? You think you're going to be able to finish this evening?
Yeah.
Cool.
Hopefully.
Get the thumbs up from Marla. I can't see her, but I know she's doing well. And I definitely got the thumbs up from Cassandra. Awesome.
The last experiment took like 10 hours.
The last one,
That's so true.
number 12?
No, I meant the last.
No,
Last
number
week's
2,
experiment.
I spilled my 60% solution 3 times. It was horrible.
Oh, lab number 2.
yeah, lab number 2.
Oh, damn. I thought you
It
were
was
talking about activity
horrid.
number 2. It's like, no, it didn't take any time at all. What are you talking taking out? Yeah, that one takes, just making the solutions takes forever.
Yeah, for sure.
then
Like
recording
those-
the
all the
microwave
numbers.
Those
oven.
last 2 are really hard. The 50% and the 60%. Those are
Yeah.
a pain to make because they do not want to go into solution.
It's like almost syrupy at the end too.
Well,
and
it
then I
is. I mean,
spilled it.
That's what syrup is, right?
Yeah, it is.
Syrup is just is really, really saturated water with a ton of sucrose in it. So yeah, it gets thick.
Mhm.
Oh,
And then I have to clean up my desk again 2 times. No, 3. Yeah.
Oh, you got sugar spilled all over your desk? And it
Oh
made it-
yeah.
got all crusty and nasty.
Yeah.
Oh,
I was like, damn it.
so you know how you say that acids aren't as, if you compare acids to bases, acids are more, or bases are more toxic to you in terms of like your skin, right?
Well, it depends on the acid and it depends on the base.
Okay, because you know, there's
like a strong acid like HCl and a strong base like sodium hydroxide. Sodium hydroxide is a strong base because when you dissolve it in water, all of it becomes sodium ion and hydroxide ion. It's just that hydroxide ion is a little more dangerous for it dissolves organic molecules better than HCl does. And so we're basically made from organic chemicals. So that's really why it's a little more dangerous than HCl. But if you have like super concentrated HCl, that will burn you.
right, because I mean, I've heard of, it was interesting you said that, just because I've heard of a lot of, well, kind of unfortunate acid attacks. So, you know, they'll you know, get bleach or they'll get some sort of really strong acid and they'll
Mhm.
pour it on someone's face, splash it
Yeah.
on someone's face,
Yeah,
and then they're
women in
just,
Afghanistan in particular. Yeah,
yeah.
so that you would use, so that wouldn't be 1 molar HCl. You would use something much stronger, like
Oh, I see.
5 or 6 or 7 molar. So concentrated HCl, like the highest you can get is like 14 molar. So that means it's 14 times more concentrated than what we were using. So
Oh,
that will burn you very, very quickly. But a concentrated base would be even more dangerous than a concentrated acid.
oh,
Because that would, like the acid you can wash off, but basically if you get like that much base on you, you wouldn't have time to wash it off before it's just started dissolving you.
oh, wow.
So nasty. So anybody have any questions about the experiments they're working on? They need help. Man, Lisette, you look like a professional, man. Where'd you get the lab coat? That's awesome.
I think I bought it online last year for another lab class.
Man, you look like you're a professional engineer or something in there.
I'm more afraid of spilling stuff than anything else.
Yeah. Yeah, especially when you have if you have other people in the house, you don't want them coming across. Yeah, I got 2 dogs and a 12-year-old.
Oh
I
my
don't
gosh.
want them
Yeah,
coming
no,
across
thankfully I have no pets at this
hydroxide.
time.
Yeah, bad.
And my husband knows to stay away. He's done chemistry before. So in my kitchen. So I have a painter's tarp thing up or
Oh
under.
man, yeah. It looks like you've gone all out.
Yeah. I mean, I've at least only spilled water so far. So nothing serious.
Professor, I have a question.
Mm-hmm.
So do you know what time you're gonna post the video tomorrow?
Probably by about noon.
Wait, what did you say? Sorry.
Probably by about noon.
Okay, that's perfect. Thank you.
Yeah. So Karina, you may want to like wear a coat or something when we're dealing with these kind of nasty things in the future. Because I see you got gloves on. That's great. But you don't want to get your shoulders burned or anything. Okay.
Professor,
Yes.
I have a question. So you know how like we are renting the lab kit and then like some of the stuff like we can't not like return it. So like
Oh yeah, that's fine. Yeah, basically what all they really want returned is like the glassware, like all the chemicals they're just going to toss because
Okay.
we can't reuse those because they might be contaminated. So we don't want to run the risk, and because copper sulfate costs nothing. I mean, so that's not a big deal. It's the glassware and the thermometers and that sort of thing. That stuff is expensive. Like just one of those like a 25 ml flask is like, $10-15. So
okay, thank you.
we'll be able to use those again. All right. Anybody else have any questions? Has everyone finished all the dangerous ones?
Nope.
Oh dear. Vera, what are you working on?
Well, I'm just going one by one. So I finished 4 and I'm up to 5.
I see you've got your watercolors made,
Yeah.
food coloring.
I forgot. You said that it's okay if it's not exactly like 1 gram of sugar, or was it 2
Oh,
grams?
if it
So-
says 1 gram, what that means is more than half a gram, but less than 1.5 grams, right? If it
Okay,
just-
'cause
if
I
it
got
just says
1.10.
1 without any decimal point or anything,
Oh, okay.
that's all it means. Just get close to 1. If they really wanted you to have like exactly 1, would have said so.
Okay,
Yeah, so if it calls for 1 and you've like tapped out like 0.9, fine. Don't spend a lot of time trying to get it exact. That's close enough.
I'm still having trouble. I mean, the experiments are fine, but it's hard. It's still kind of hard to figure out whether it's a chemical reaction or a physical reaction.
Yeah, like for instance, what do you think that the formation of the gel is?
Oh, that one would definitely be a chemical one, wouldn't it?
Why is that?
Because both were just solid, right? And then,
Mhm. But it was a solid before. And it's a solid now.
oh,
The only difference is the amount of space it takes up,
oh, I see.
right? So it didn't change color.
It just
Didn't release
expanded,
any
I
heat.
guess, right?
Really all that happened is that it changed shape. And like you said, if something changed shape, is that a chemical reaction?
Oh, I see.
No, it just got big. It's like when you take, like you get one of those dried up toys for your kid to play in the tub. When they're really little, they come in the big pill and you toss it in
Oh,
the bathtub
Orbeez?
and it goes blows up into like a big
Oh.
sponge or something. That's really all that happened there.
Okay.
It just absorbed water. So that solid absorbed water. It didn't change chemically in any way. It just absorbed water.
So like sugar water would still be just, it'd be more physical than it'd be chemical.
Right, because it's still sugar.
Still, okay. That's
It's still
okay.
sugar. We haven't broken that one's a little difficult just based on the observations, because you dissolve the salt in the water and it doesn't really make it that much. It doesn't change color, it doesn't change temperature that much. Or did it? Did it change temperature much? This probably should change a little bit of temperature. When you dissolve the salt, did that change temperature for people?
I'm still working on that part.
Okay.